In this video, we're going to look at approximating the distribution for the sample proportion for large samples. So we know that as the sample size increases, the shape of the probability density function changes, and we know this from our work with binomial distribution because the probability density function for the sample proportion is a binomial distribution. And if we're working out binomial probabilities for large values of n, then we're calculating that using our combinations formula, which can be really difficult to work with if we're working with large numbers. So if we had 1,000 C100, that's difficult to calculate by hand, as is some fraction to the power of 100. Difficult to calculate. Well, not difficult, just cumbersome, takes a long time. So we use the fact that the shape changes in a particular way so that we don't have to do this calculation by hand. So let's start by looking at how the shape of the distribution changes as the sample size gets bigger. So we're going to look at a sequence of binomial distributions, all with a probability of success as 0.1, and we're going to look at the shape of the distribution as we change the sample size. So let's start with n is equal to 10. So this is what the distribution looks like. It's definitely skewed, and for a sample size of 10 from our very, very large population, we can see that we start to get an indication of how the large population is distributed. Because in the large population, there's some underlying distribution, and our sample that we've taken is hinting that it might look like this, the overall population distribution. So let's increase our sample size from this very big population with the hopes that we will get a better idea of the distribution of the large population. So let's increase our sample size. So this is our sample distribution with n is equal to 20. You can see that it is still skewed, but we're now starting to get a little bit of a shift in where the peak is happening here. So it still looks like the population that we're selecting from is heavily skewed to this end. But let's increase our sample size, because if we increase our sample size, we'll get a better indication of what the overall distribution looks like in the population. So let's go bigger again. So here's our distribution for a sample size of 50. So our graphs are having to get smaller because for a sample size of 10, we need to go to 10 here. For a sample size of 20, we need to go out to 20. So for a sample size of 50, we're out to 50 here. But you can see that what started off in our 10 as being really heavily skewed down to the lower end here is now starting to have a peak that appears to be moving across this way a little bit more. Still heavily skewed down this end, but much more of a shape appearing here. So let's go bigger again. So here we have a sample size of 100 from our very large population. And because we've got a bigger sample size, we'll have a better idea of what the underlying distribution is for the population. And you can see now we're starting to get a very familiar shape. So let's up the ante and have a look at a sample size of 1,000. So here it is here. And it is very squished because we need to go all the way up to 1,000 here. But if we zoom in down this end and have a look, let me just zoom in and have a look, come on. You can see that what we've got here is a nice smooth bell-shaped curve which pretty much looks like a normal distribution. And for the normal distribution, we know that the mean sits right underneath this peak. So our mean is here. So our mean for this population is 100. Our standard deviation we could also work out by the shape of the curve, but there are ways to predict both the mean and the standard deviation from our original values of n and p, because we have our n is equal to 1,000 and our p, which is our population proportion, is equal to 0.1. Can you see a way of working these two to get this? Of course, so this is a binomial distribution. So if we were to work out these values here are our values of x. So these are our values of x values. So because our x value is distributed binomially with an n of 1,000 and a p of 0.1, our mean for our x value is n times p. But we're not after the actual x value, the outcome. What we're looking at is the sample proportion. Okay, so we need the sample proportion. We need p hat for this. And p hat is our x value divided by our sample size. And so our p hat for this, for our mean, is the x value is 100, the n is 1,000. So our p hat value for 100 out of a sample of 1,000 is 0.1. So our mean for p hat, our expected value for p hat is p, and that is our mean for our underlying normal distribution. Let me put this down here for you. So the underlying distribution of the large population, so the population that we're drawing the samples from, is a normal distribution. So the larger the sample we take, the more it's going to look like the population that it's coming from. And we've shown that for a large population that's got where you're doing a binomial distribution, when it gets finding a binomial distribution in your samples, when you get really large samples, it actually starts to look like a normal distribution. And the mean of that normal distribution is related directly to the expected value for the binomial distribution. And if the binomial distribution is a proportion instead of an x value, then it's the expected value of p hat, which we know is p, the population proportion. And we also know that the standard deviation for that mean population will also be related to our sample proportion for p hat, which has this formula here, where n is the sample size that we're using. So we are using exactly the expected value for the proportion as our mean value for this normal distribution, and exactly the formula for our standard deviation of p hat for our standard deviation for our normal. And so this allows us to use a normal approximation for p hat. So we can say that p hat is approximately normally distributed, and our normal distribution has a mean and a standard deviation. And our mean that's going to go here is our population proportion. And our standard deviation that's going to sit in here is this formula here. And remember, if you're using this notation, that's actually the variance. So what this allows us to then do is to use normal distribution to calculate probabilities for p hat. Now this might seem like a little bit of a convoluted way to do these things, given that you are able to use your CAS calculator to work with your original population proportion and your original sample and a binomial distribution, and the CAS calculator would do everything for you. But this idea has two reasons for doing it. One, thinking about the underlying distribution of a particular characteristic within a population. And for large populations, that is generally a normal distribution. But also, in the old days, we used to have to work these things out by hand, and doing a binomial distribution with very large numbers by hand is extremely tedious. But we had a table of values for standard normal distribution that we could just look up and then do our normal work on normal distribution to find probabilities for particular x values. So that's what we're going to practice doing. We're going to practice finding an approximate probability. So this probability will be an approximate probability. We're going to practice doing that using normal distribution. And to do that, we need to first find out our mean and our standard deviation from the information in the question. So let's have a go at a question. So in Victoria, 9% of people over the age of 18 hold a motorcycle licence. What is the probability that in a sample of 20 teachers at your school that more than 10% hold a motorcycle licence? So what we're looking for here is the probability that p hat is greater than 0.1. Because we're after the probability that more than 10% of the sample, so this is our p hat value. And remember, we're working with the fact that our p hat is normally distributed. Okay, so the first thing we need to work out, if we're going to use our normal distribution, is what our mean is and what our standard deviation is. So we know that our mean is equal to p hat, to p, our population proportion, and our population proportion in this question is given up the top. In Victoria, 9% of people over the age of 18 hold a motorcycle licence. So our p value is 0.09. Our standard deviation is our standard deviation for p hat, and if we insert our values for p and 1 minus p, our n value goes here at the bottom, and from our question we've got a sample size of 20 teachers, and so that n is replaced with 20, and now we have our mean and our standard deviation for our normal distribution. So we can go ahead and use our CAS calculator to work that out. And in your CAS calculator, you can actually put this formula in straight into the input line. You don't actually have to work this out. And here's what I did with mine. So the probability that I'm working out is that p hat is greater than 0.1. So my lower bound is 0.1. Upper bound for a normal distribution is infinity. My mean is my population proportion. You can see I've put the formula in here. And what you just need to be very, very careful of when you do this is, if I zoom in a little bit, you can see that my formula has a bracket here at the start and a bracket at the end, so that it is all square rooted. So the square root takes that bit there, which is what that bit is underneath. So finally, we get to the fact that the probability that p hat is greater than 0.1 is 0.4, let's say it's 4. So the probability that more than 10% of the teachers at your school, or 10% of a sample of 20 teachers at your school hold a motorcycle, is 0.44. So at least 2 of them have most likely got a motorcycle license. The other sort of thing that you need to watch out for as an indicator for the fact that this question is a normal approximation, they call it a normal approximation, is that in the question, and I haven't done it here, but in the question it will say up here, when it asks for the probability, it will say the approximate probability. And if they ask for the approximate probability, then you'll use a normal approximation. Haven't seen it in an exam yet, doesn't mean that it's not going to happen, but that's an indication that you should use the normal approximate. The final sort of question that you see around this idea of a normal approximation is where they tell you, or they give you an indication that a normal approximation or an approximation of the distribution has occurred, and then they ask you to find either the sample proportion or to find the sample size that was used to come up with the mean. So it's really just playing around with your sample proportion formula that contains your population parameter and your sample. So generally the question will give you information around 2 of these and ask you to find the other. Now sometimes the information that they give you is actually kind of hidden away in the question. So in this question here, let's just read what it says first. The distribution of p hat from a large population has a mean of 0.8. So it's from a large population, the mean is 0.8. So we know that the mean is 0.8, and that's actually equal to the population parameter. So we can put 0.8 in here and here. So we've already answered one of the questions that was asked. So p is equal to 0.8. The second question that they ask us is to find the sample size, and if we continue reading the question, so we've got a mean of 0.8. It says that the standard deviation is 0.1. The standard deviation is 0.1. So that means we can put 0.1 here. And now what we've got is an equation that says 0.1, and everything else in the equation is filled in. So 1 minus 0.8 is 0.2 over n, and now we simply just solve this on our CAS to find the sample size. And so our sample size is 16. So in these questions, what you're looking for is you're looking for a hint around our p-value, our population proportion, and whether they give you a standard deviation or a sample size, but they will give you two of them and ask you to find the other one.